Hello, my name is Marilyn Zecher. I'm coming to you from Rockville, Maryland. I'm here tonight for Build Math Minds to talk about strategies and models for the inclusive classroom. I do teach two multisensory math graduate level methods courses on how to reach a neurodiverse population in classrooms, individual settings, all sorts of instructional settings. Your warm-up is to think of three of the most common instructional strategies that you use to support students in neurodiverse instructional settings. Oh, and you can't use a calculator as one of them. Today, our inclusive classrooms are really diverse in the population of students we meet and serve. They may be inclusion classes, they may be general education classes with neurodiverse students in them. They may have learning differences, challenges, language challenges, and teachers have to find ways to meet the needs of all those students. We also have a diversity of instructional settings. We have general education classrooms and small groups within them, sometimes with a co-teacher teaching a small group while the rest of the class is doing something else. You might have a dedicated classroom. You might have resource room, individual intervention settings, pull out, push in, one-on-one tutoring. So we have a great diversity of instructional settings as well as a diversity of students. So picture, if you will, your typical student with special needs. It might be in your inclusive setting. Is this a student with a disability, with dyslexia, attention deficits, executive function problems, hearing or visual impairment, second language learner you're teaching in English and maybe they're doing the math computationally in their home language, a student with a complex neurological profile or cognitive profile. And we all know that in almost every class we teach, we have students with unfinished learning, students who need to have certain concepts reviewed before they can move on to grade level content. There is no typical in an inclusive classroom. We all bring baggage to the classroom, some days more than others, and we look at evidence-based strategies to try to help us to lessen the impacts of these challenges. Inclusion actually means that we're using methods that are appropriate for all, though they may be essential for some. Just for a moment, I want to talk about accommodations versus strategies. Accommodations are something we use to level the playing field, make participation easier and equitable, but they should not change the content. And it allows us to see multiple options for student output, what we see as a result of our instruction. Instructional strategies that I'm going to talk about tonight are teacher-centered. They make participation easier and they don't change the curriculum or content. They don't change the concepts. They create multiple options for content input. And that means that the teacher has to be cognizant of how the instruction impacts a variety of student characteristics: visual, auditory, tactile, kinesthetic, whether the student has good working memory, poor working memory, long-term memory issues, retrieval issues, processing speed or visual or auditory issues, attention, executive function. We have students with spatial and directionality issues, fine motor control, deficits like dysgraphia. We have to be cognizant of all the ways that students receive information, but also how they process that information and how they retrieve it. So our instructional strategies can be evidence-based. They can come from neuroscience, educational research, best practices in math education. We have to look at the efficacy of what we're using. I'm going to start first with the science of learning, the body of research that comes from three fields: cognitive psychology, neuroscience, and education. We always want to learn how the brain processes information. We want to identify the most effective strategies for teaching based on the underlying cognitive processes involved in learning. The science of learning examines how the brain processes information, memory formation, attention, retrieval, and problem solving. And we're looking for what is replicatable from research that's effective. And we want to translate that research into actionable teaching practices that optimize learning for all of our students. These are the core principles of the science of learning applied to almost any field. We all know we don't study for a test just the night before, so spaced repetition over time really improves memory retention. Interleaving, mixing up the types of problems that students address in one setting so that they constantly have to retrieve information from various memory sources. How do I attack this problem? Well, this one's different. How do I attack that? What is the model of the operation I'm performing here? What does it mean? What does it look like? We mix them up so that students constantly are retrieving memories from different parts of the brain and from different sources of information. The student has to have metacognition and be aware of their own ability to learn and what they need to do to optimize their learning and their performance. Retrieval practice, we know that as students retrieve information, each time they do, they strengthen neural connections. And the more times they retrieve something, the stronger it becomes in long-term memory, which is accessible for applications and problem solving. The last of them begins with one of my favorites, dual coding theory, where we wed images and language to help us remember things. It's helping us to see the math. If you think about some representation of math, like measuring cups for baking, the difference between 1 cup and a half cup and a quarter cup, those are visual memories that are associated with math concepts, measuring tools, and fractions. Elaboration means teaching from known to new. We want to link new information to previous learning. That's one of our core concepts for intervention. At the beginning of the lesson plan, we can begin with a review of something from a while back, but we know is a foundation of what we're teaching that day. And just bringing that to the fore, having students retrieve it, even just for a few moments, a few problems, can help them to link to new learning. And finally, concrete examples, using them to anchor information that is more conceptual in nature. Another source of evidence-based strategies is from our Institute for Educational Sciences, the What Works Clearinghouse and its practice guides. They list evidence that have maybe sorted from 4,000 studies down to 100. And they list the evidence as strong evidence to support its use, moderate evidence, or weak evidence. Those specific recommendations are at the end of my handout for this presentation. And these ideas, all of them, can be applied to instruction in mathematics. So now some strategies for engagement. All students must participate in unison for small activities. Think of having a yes and no card on each student's desk. And instead of saying, who would like to answer this question and looking for hands to be raised, all students answer. They hold up the yes or the no or some information bit that you've given them. And that way you can see that all students are paying attention and they're all engaged in the learning. Gross motor activities, like the one you see here. These are participants in one of my classes looking at transformations of quadratic functions, where here we're modeling vertical stretch and vertical compression, and we're doing it with gross motor activities. I use these a lot in algebra, but they're also really useful as gross motor activities in elementary school. Think of the directionality and sequence for multi-digit multiplication. The ones times the ones, and the ones times the tens, and the ones times the hundreds. Using large motor muscles often anchors something in long-term memory. Choral response, like keywords for procedures. Things like collaborative tasks. Here we have students, one student leading other students in decoding large numbers, knowing that the tens and ones are often read together as a unit. So we would say 79,623. And this student is leading others in decoding those large numbers. Collaborative tasks like working together. Here, these students are lining up cards with numbers on them and organizing them from least to greatest. And here they're deciding which vocabulary words from the semester fit with others. The students were just given a pile of cards and said, here, organize them in a way that makes sense for you. And then the teacher just stood back and listened. All of these are good, different activities for engagement. So our first topic tonight is multiple representations, and you're going to see this throughout all of the research. Students need to see more than one representation of a concept. Notice I'm not talking about algorithms. I'm not talking about explicit instruction in do this, and then do that. Not moving numbers around on a page, but actively engaged in having a way to show what the operation or the concept means. And when we use multisensory activities, we're creating memories in different parts of the brain. Physical, kinesthetic activities can help create kinesthetic memories, auditory memories, visual memories. All of those come together, they converge in the brain, and they help to make meaning. So the more the brain that's involved in the learning, the stronger the associations for memory and retrieval. That's something we want to remember. Concrete manipulatives do have a place. Almost every curriculum endorses their use. The problem is that most teachers don't have training in using manipulatives effectively and efficiently. They're not to be used as inefficient calculators. You can use them for problem solving, but their main purpose is to explicate concepts. What does this operation or this concept look like? What am I doing with the quantity? Can I physically do that with this manipulative to demonstrate what the math looks like or what it feels like with directionality and sequence and the meaning of the math, the meaning behind the math? One model that's used frequently is the concrete representational to abstract instructional sequence that can be used in one lesson with one concept in your new introduction part of your lesson, but it can also be used in any order for retrieval and intervention. You might teach a concept like addition is putting together, and then you might draw a picture, and then you might use just numbers at the abstract level. But follow-up, you might work a problem with numbers and say, prove it with a manipulative. You can use it to create the manipulative and then model what you've done with that at the abstract or pictorial level. The representational or pictorial level is the portable memory. And in fact, the practice guide on problem solving says that if students can draw a picture, they can usually solve a problem. So we need to offer explicit instruction in drawing efficient pictures to solve problems. So manipulative use, they must be efficient and effective for what you're teaching, and they are not inefficient calculators. And the goal of using manipulatives is to get rid of them, to move past the need for them. But you can always go back to manipulatives to review something. And I use them up through algebra and find that my students remember more. Yes, they're a little messy and time-consuming, but you will do less reteaching, and you'll find that students remember more. So, key to using manipulatives is a process called simultaneous processing. So here you see people who have built quantities on a place value mat. They touch the manipulatives as they read the quantity with their hands. Then they may hear and see when they speak out loud or when they think the words. They're also using receptive language. And so as they're saying things, seeing them, touching them all at the same time, they're building that multimodal memory so that it aids retrieval. So this builds visual representations in language for later reasoning and applications, including mental math. You want to create the memories so that when you come back to doing it mentally or just with numbers, the students remember what quantities and the manipulations look like. So here's one strategy I love from about second or third grade on, and I've used this up in intervention for middle school students. Give a student a bag of loose craft sticks. You can do it for individuals or pairs of students for collaborative learning. Students must decide the quantity without counting. They could estimate, and then they begin by placing the craft sticks in tallies with a bundle when they get every 2 sets of tallies and place them in the appropriate place on a place value mat. With my students, I sometimes will say, how many tens can you build in 2 minutes? That's a good use of a timed activity. Then, as they build the quantities, they build the numbers of tens, I have them decide how many sticks they have in their bag. Or I might have them just build as many tens as they can in 2 minutes and then come back the next day and do the same thing. And the day after that, how many hundreds can they build from the tens they've made? Students describe and write the quantity in both standard and expanded form. Using your hands, you can say, standard form tells me what a number is made of. Expanded form tells me what a number is made of, and standard form tells me its name. So expanded form tells me what its name made of in terms of place values, and standard form tells me its name. Simultaneous processing and numeracy. We know that counting begins with touching, just as a child touches and counts with their fingers. Visual memory can be achieved with pattern recognition as we learn the composition and decomposition of quantities under 10 as we build them. Our linkages include quantity, symbol, and name, where in reading we might do sound-symbol correspondence. In math, we're doing the quantity, 4, the symbol, 4, and the name, 4. So we want to learn the composition and decomposition of all quantities under 10. Here you see a young child looking at her fingers, maybe counting to 5. This little boy has counted 4, and the 5th one, if he crosses it, it's kind of like the origin of our tally. But these are tactile and visual pieces that we can use and strategies for instruction. Notice the flat glass marbles or jewels placed on a blank domino. A young child matching the dice patterns to the quantities and naming them, seeing what 5 is, and then rearranging those flat glass marbles on the space to do the addends of 5. Having the child put 5 sticks with a tally in the ones place. And by the way, once you teach 10, 11, and 12 in kindergarten, you are teaching place value. So that's something to keep in mind. This bowl here represents a dice game I invented called Make-A. And even in kindergarten, you can play Make-A-5. You roll 5 dice. If you get a single die with 5 on it, it's worth 1 point. But if you get 2 dice that sum to 5, you get a set of tally marks like this for your score. Every time you roll the dice, you either make 1 point or you make 5 points. In this case, this hand is worth 6 points. 5 for the 2 plus 3, and 1 point for the single die with 5 on it. Now, as you start to record your score in tallies, you end up circling 2 sets of tallies to make 10 and counting by tens to sum up your score. But visual patterns like dice and tallies, and in this case, unit cubes from the base 10 blocks made into a pyramid, you can always tell the quantity because it's based on a renewable, repeatable pattern. Here you have a pipe cleaner with large wooden beads, and the child can literally move the beads to show the addends of 5 and to sum to 5 to process addition and subtraction both. So we want to think about that quality conservation of quantity, that the quantity is the same even though the configuration may change. This idea of 5 flat marbles turned into 2 marbles plus 3 marbles, but it's still a total of 5, is the idea of conservation of quantity. The arrangement may change, but the quantity stays the same. That is taught in kindergarten, 1st and 2nd grades, but it's a foundational concept for fraction with equivalent fractions and for algebra. Think of the different forms of linear functions. Think of the different forms of quadratic functions. The arrangement may be different, but the quantity stays the same. Look at these pictures and look at the various ways that we can use multisensory strategies to teach things. Here we have, this is my pattern of 5. The child has to write the numeral 5 and make a dice pattern of 5 with stickers. These are foamy sports ball stickers or the flat glass marbles, and then explore the different ways to make 5. Here, we're going to link the tally of 5 to making 50 with a tally of 10s. But that repeatable pattern is going to continue so that students can see that pattern and recognize not only 5, but larger quantities with that 5. That's our first site for informal bundling. Here, we've actually built a tower of 3,000 craft sticks. Each 100 is a different color, and each 100 is made of 10 tens. Now, you might think that's a little bit silly, but I have 4th and 5th graders. I have adults in my classes who like to pick that up and feel the mass. We don't do a very good job of teaching magnitude in this country, at least not the visual properties of it. Here we have multiplication, and yet there's 10 at the bottom. So in other words, we're starting with 10, and then we have a constant rate of change by 2. We're going to be talking about that a little later, because that's a concrete model of slope-intercept form and a linear function. Here we have a multiplication array. This is not the typical array that's taught in classrooms, because this one has the factors on the outside of the array and the partial products in the middle. This one is 4 groups of the quantity 13. And so look, we have 4 groups of the 10 for 40 and 4 groups of the 3 for 12. 4012. What an interesting number, 4012. I bet I could simplify that as 52. So even in the lower grades, we can talk about numbers in improper forms that do not follow the rules of place value. We can talk about simplifying numbers quite early using manipulatives. Here you see polynomials. This is actually f of x notation. If x is 2, x squared is 4, and x cubed is 8. But if x is 3, then x squared is 9, and x cubed is 27. And if x squared is 16, what was x? And what would x to the third be? You can use these for problem solving, combining like terms. So manipulatives can offer visual reference and visual meaningful components for students to remember when they're doing mental math and applications. So we have fractions, we have multiplication and division tools, we have name that quantity. Can you name this as shown and as simplified? I have 4 halves, and simplified it's 2. I have 7/4, which can be simplified as 1 3/4 as a mixed number. So we can use visual dictionaries, concept cards. Over here, this brown one, well, wow, that could be the beginnings of division, where I'm making groups of 2 from an initial quantity. But it can also be a decreasing linear function model. So manipulatives can form lots of visual patterns and representations that students can use later to rely on for reasoning mathematically. We do use explicit instruction in concepts with multiple representations. This appears in the What Works Clearinghouse practice guides again and again. It often includes manipulative objects at the concrete or semi-concrete level to explicate those math concepts. And so when students work with those multiple sensory areas, they are building those memories in different parts of the brain to aid retrieval. One of the concepts that's seminal for us is subitizing. Some people like to think of it as a core deficit in mathematics. It's the automatic recognition of quantity. And science has shown us that the human brain begins to quantify before it acquires language. It happens in the high chair when students are visually assessing more and less from small quantities. Human brain, we think, generally can recognize up to 4 without counting, but anything after 4 has to be in a pattern. This is why some of the traditional methods we're using for representations in math don't work as well. For example, 10 frames are great for building the addends of 10, not as great for building the addends of 7. So we look at two types of subitizing, perceptual and conceptual. In perceptual subitizing, I see it, I know it, that's 5. I know that that's 9 because it's a pattern I recognize. Conceptual subitizing is really important for the upper grades. That's where we recognize sets within a set. We recognize 5 and 4 making 9. Now, the article is called Subitizing. What is it? Why teach it? And you can find it online. It's a good read and really informative. Pattern recognition is something we're going to find in all of the animal kingdom. Here we see a mother zebra who takes her baby away from the herd until it recognizes the pattern of her stripes. It's really dangerous for a mother and infant to be alone, but she has to make sure that that baby knows her stripe pattern. We know that visual patterns can aid students in retrieving and applying numeracy. Each pattern creates a unique visual memory, and this is one way we can support subtraction. So, for example, if I know that 7 is made of 3 and 4, that's one decomposition pattern. 23 minus 7. Wow, take away the 3, I'm at 20. Take away the 4, I'm at 16. But if it's 42 minus 7, I might subtract the 2 and then 5. Those visual patterns from dice and dominoes can really help us to acquire strategies for mental math. How quickly can you name these quantities? Name this one, this one, this one, this one, here, here, and here. Did you have to count any of them? And how did you recognize this one? Did you see it as 3, 3, and 1? Or did you see it as 5 and 2? And it doesn't matter. The fact that you can name that quantity is good numeracy. So pattern recognition exists at all levels of math. I said this one is a linear function. These are all visual representations of the addends of 7. Here are your square numbers on a times table chart. And we can use that chart later to look at it and trace perimeter and area of squares and discern the pattern, the equation. Here we have that division or linear function model decreasing. The pattern, the visual memory of alternate interior angles or vertical angles, and our quadratic functions. How is it that we get vertical stretch? How do we get vertical compression? What part of the equation does that? And can I model it with my body? Multisensory representations and pattern recognition exist in all of our major hierarchical concepts in math. So imagine place value. We have our ones, our tens, and our hundreds and our base 10 blocks. But how have you thought of using the 1,000 cubes to create 5,000 and the 1,000 blocks to create 30,000? So we can literally decode this number as 35,358. And by placing our unit cubes in pyramids, we make it easy to quantify everything under 10. So we base consistent patterns on established visual and tactile imagery to enhance quantity awareness and magnitude. Place value concepts are a second level up from numeracy that must be in place for our students. It's how we organize quantities for automatic recognition. Place value is just subitizing on a higher plane. Always use graphic organizers to anchor students in the concept you're studying. So we would have our tens and our ones and our fractions of 1. Here's money place value mat for ones, tens, and our 100 pennies, which helps even our lower grade students recognize how to make change. And here, when we get to decimals, we're going to be using them and linking them to the concept of fractions. They are decimal fractions until we get to irrational numbers. But we want to use patterns that are visually replicatable. All of these quantities here, you should be able to read. This one, 5 and 4. This one, 5 tens. Look at our 5 tens with base 10 blocks. And this one, our 10 and 5 ones. And that leads us to understanding what expanded form is. So when we want to compose numbers, we actually want to use manipulative objects. I'm going to take just a few moments here to illustrate something else. So here under my document camera, I have my ones and my tens. In younger students, we're going to be building our second set of tallies here, noticing that our place value concept is that when we get 2 tallies, when we get 10, we bundle. And then it gets moved into the tens place. But what I wanted to introduce for you tonight is the idea of writing our teen numbers, which is very problematic for our young students. The number 11 comes from Einlief in Old German, Old High German, which actually goes back to the founding Germanic languages. It's one left over after I counted my 10. So it's literally 10 and 1. But we say the one left over after I counted my 10. And so 11 is one left over. 12, we think from the Old German, was 12. It was 2 left over. And notice that everything that has to do with 2 starts with TW. So we're going to have 2, we're going to have 12, we're going to have 20, we're going to have twins. We notice that that TW is there in all of our representations. 2, 12, 20. So 11 and 12 have unique names, and we want to work with our students to write the 1 in the tens place and the 2 in the ones place. The way that we're going to help students remember it is to say, what is it made of and what is its name? 12 is made of 1 10, 2 ones. Its name is 12. When we get 3 ones left over after I made my 10, I don't need to count the 10 again. I've already counted it. So it's 13, and the teen was their word for 10. And so 10 and 3 is named 13, touching it, simultaneous processing as I say it. You want to go ahead and build all the numbers up to 20 this way on the place value mat. And you want to take it to a number line. Number lines are critical in preparing students to know their number system. So as we build the numbers, look how easy it is to recognize the quantities that are here. I see that that's 5. It was 5 left over after I counted my 10. Its name is 15. Now, as I build other numbers, and with students I would build each one, look how easy it is to know what that quantity is. You do not get that kind of representation by stacking a line of cubes. Remember that if the human brain can recognize up to 4 without counting, everything over 4 needs to be in a pattern. This is going to help your students recognize quantities as you build 2-digit numbers. And remember that we can always have our students build numbers, name them, describe them, tell expanded form and standard form. What is it made of and what is its name? Those visual memories will help them quantify, which leads me to one last jump ahead thought. When we're teaching regrouping, we are going to be building numbers that are going to not obey the rules of place value. So if I add on to the number that's there, and I add more, I can see that my ones place is getting too crowded. What do I have to do to simplify this number? So for example, this is 3 tens, 13 ones in the ones place, 30, 13. What a silly number. What could I do to make this number more simple to recognize? And I would bundle that 10. For subtraction, if I have a quantity and I have to subtract 9, we are no longer using the words borrow and carry because, honey, we ain't giving nothing back. The question becomes, do I have enough in my ones place value to subtract 9? No, I don't. Where can I get what I need? I have to decompose a 10. And what we do with our manipulatives exactly replicates what we do with the algorithm when we are teaching subtraction with regrouping. So I'm going to create an improper number, one that is not simplified. It's, as my fifth graders in Louisiana said, it's complexified. So now I have 2015. What a silly number, but I had to create it in order to subtract 9. So we model what the concept of decomposing a 10 and composing a 10 looks like. They build it, they describe it, they name it. And once they've interacted with that, it's much easier to move to the representational and the abstract forms. So keep in mind that everything you're using explicit language for the concepts. We're not giving directions about what to do, but we're helping students to visualize what it looks like and what it means. So composing magnitude, here we have a lower grade class. This is third grade, third or fourth grade in an independent school. And they've built the place values. They've modeled them. They've shown how they decode them, what the comma's name is. This is my middle school class, my summer intervention group. This is where the students come in and they see a quantity and they have to decode it. They have to write it in expanded and standard form. And then based on that, I'll have an activity where they maybe discover something, they problem solve with what they've found. So we can use these representations to guide our imagery. Here we have our 3000 again. This is my Math 2 class where we have built scientific notation with the base 10 blocks. And Julie here is standing in the middle of 1 in a million. This is a school where they've done this, and the student of the week gets to go to the library and stand in the middle and be 1 in a million. So they get to see the pattern and the symmetry of our place value system, using it all the way up through middle school. So reasoning and mental math, once they have that visual imagery, you can have them build a quantity for a warm-up and then double it or halve it. You can do mental multiplication. Look at this quantity right here, 1,234. Could I double that quantity? What would it be? It would be 2,468. Could I have that quantity? Well, that's going to be a little bit of a problem. That's a great reasoning activity for students to use, either from a mental pictorial representation or just from the numbers in their heads. It depends on the students you have. But using these concrete examples and pictorial examples, you're helping all students to master the concepts. We want to transfer what they know from that visual and tactile imagery into reasoning mathematically and problem solving. Strategies for multiplication and division. We can build models with linking cubes or unifix cubes, and we look at the difference. What happens when the base changes, when it goes from 2 to 3 to 4? And so as we look at that, we can also set them side by side. We can see what their shared common multiples are. We can build multiples of 3 with craft sticks. We can build arrays with the factors on the outside and the product in the middle. Here we're doing 2-digit multiplication. 2 groups of 12 makes 2 groups of the 10 for one partial product and 2 groups of the 2 for the second partial product. In the 4th grades and up, we move that also to the area model or box model of multiplication. This is a really good model for many of our students. It's place value based, and I can see why I regroup in multiplication. I can see what my partial products are. One of the reasons it's such a good model is this is one of the models we use for polynomial multiplication in algebra. So teaching it early just provides that linkage. And we can then, for intervention, go back and show it with whole numbers and then move it to variables. But it's really wonderful for our younger students to see the various representations of multiplication. So some of the things we can do include that gross motor practice in the multi-digit multiplication algorithm. Using our simultaneous processing, as we say, 4 groups of 10 is, we touch it, we say it, we build it, we construct it, we describe it, and we know it. And 4 groups of the 3. We want to scaffold fluency development and use it with applications. In an inclusion class, you're going to have many students who need to go back and continue working on fluency development for math facts. Math facts are important. They free up working memory for applications, especially as they go toward middle school and high school. And so I know there are some people who disagree with me now. I'm sorry about that, but those of us who teach at the higher level as well know how important it is for our students to be able to reason mathematically. And the more comfortable they are with that multiplication and division, the more comfortable they're going to be in not overthinking things at the algebraic level. So we do want to build fluency. And there are ways to do it in an inclusion class. I'll talk about that a little bit at the end of this presentation, but going back and reviewing targeted number facts for a period of time and using them throughout the classroom is a great way to review them and develop automaticity for small sets of facts at a time, and then through interleaving and practice, keep building on what they've learned. This is a tool called Strings with Wings. It's a wonderful multiplication tool I invented for a young lady, a 7th grader, who came to me and said, the one thing I've always wanted to learn is the 7 times table. Now you can use this for any group of multiplication facts. I tend to use them for the larger multiplication facts, though they can be used for the lower ones as well. I'm going to model a couple of applications here and show you how it can be used for reasoning. So as we go to this one, what it takes is a nylon-tipped craft lace or shoestring and 9mm pony beads. One end is, they're both knotted after you build it, and the student has to have some room for moving them. Here, I'm going to explicitly teach the multiplication a few factors, a few products and factors at a time. So I have one group of 7. Let's take the other one. And it doesn't matter whether you go left or right. I happen to be right-handed, so I'm going to move my beads this way and build one group of 7 is 7. I can see it. 2 groups of 7 is 14. I'm asking the students to move their strings and beads as they're working with me. I see, because of the neuroscience, that I can see that's 2 groups, and I associate that with 14. 3 groups of 7 is 21. I can point and count 3, 7, 14, 21. I can count up and back. I can skip count by 7s because I have a visual reference to anchor me in what I'm doing. 4 groups of 7, 7, 14, 21, 28, 21, 14, 7. Then our students are going to be saying this in choral chanting. 2 times 7, point to it and say the product, 14. 4 times 7, point to it, say the product, 28. 1 group of 7, 3 groups of 7, 2 groups of 7, 4 groups of 7. But the purpose of this is not just learning the association of the words for multiplication. And by the way, we have shown in terms of neuroscience that multiplication is language dependent. So students who have trouble with verbal, oral language, retrieving words and retrieving things in terms of words, they're going to be at risk for struggling with multiplication fluency. Whereas addition and subtraction facts can be supported by visual imagery and subitizing, multiplication cannot. And so what we're trying to do here is build some of that visual memory. Now we're going to look at applying it. If I had 21, how many groups of 7 could I make? I can make 3 groups of 7. If I had 22 beads, how many groups of 7 can I make? I can still make 3, and I have a remainder of 1. Now, the crucial part of this is to state that that's 1 out of the 7 I need to make a new group. I'm going to say that a couple of times for you, because that's going to be important when we get to fraction division. My remainder is 1 out of the 7 I need to make a new group. I can say now 22, 23, 24, 25. 25 divided by 7. I can still make 3 groups of 7 with a remainder of 4. And that would be remainder 4 or remainder 4/7. 3 and 4/7. Now, where this goes after that, I'm going to eventually, with the students, build the entire 7 times table. We don't have time for that today. But let's look at some other uses. If I had 21, I have 3 groups of 7. But if I only had 2 of those 3 groups, I would have 14. So 14 is 2 of the 3 groups that make 21, or 2/3 of 21 is 14. Look at 4 groups of 7. Can you tell me what 75% of 28 is? What is 3/4 of 28? Can you tell me if I cut each bead in half? I started with 7. I'm dividing each bead into 2 equal parts. So 7 divided by 1/2 is 14. I can look at 21 and say, could I cut that quantity into 2 equal parts? What would 1/2 of 21 be? And the student might take this, set it apart, and say, wow, it would be 10.5. Can you tell me what 28, if I multiplied 28 by 5/10, 5/10 of 28, or 1/2 of 28 is 14. There are so many uses for this tool, but the nice thing about it is that it sets up the concept. I want you to look at this one, and we said that 2 of 3 groups that make 21 is 14. 2/3 of 21 is 14. Now, could you apply that somewhere else? What would 2 of the 3 groups that make 15 be? What would 2 of the 3 groups that make 18 be? So I can do 2/3 of 15, 2/3 of 18, 2/3 of 9, 2/3 of 12, 3/4 of 12, 3/4 of 8. I use this to teach students that visual concept of taking 2 of 3 equal parts, or 1 of 2 equal parts, or 3 of 4 equal parts of a larger quantity. So we're multiplying whole numbers by fractions using a common imagery tool. So that's strings with wings. It's one of my chief tools for reinforcing and practicing multiplication and many applications with it. So models for multiplication can include engagement of students. Color in the multiples of a number on a hundreds chart, and then you can skip count with a near point reference. Use your multiplication chart to discover patterns. Look at the 6s here. 12, 24, 36, 48. 1, 2, 3, 4, 2, 4, 6, 8. 2 times 6 ends in 2. 12. 4 times 6 ends in 4, 24. 6 times 6 ends in 6, 36. 8 times 6 ends in 8, 48. And then you let your mouth do the heavy lifting. You ask the questions and the students answer. Rhythm is one of our untapped teaching tools. There's a whole strategy for teaching the 9 times table without the finger thing. I've seen 11th graders in Algebra 2 using the finger thing for figuring out their 9 times table facts. It's not necessary, but there's a little chant that can go with that, such as 4 times 9 starts with 3, 7 times 9 starts with 6, 2 times 9 starts with 1. So if you know the first digit and that the numbers sum to 9, you can get the second digit. Here you can see that our models with unifix cubes, we're showing the common multiples. So I can find the least common multiple, but recognize that there are other common multiples. And here's my array, and we scaffold our fluency development. Here, we're using our multiplication chart. And by the way, anything here is not there, not written, because it is included up here. And we're showing that property where 3 groups of 4 gives us the same product as 4 groups of 3. And students can use the multiplication chart for doing area and perimeter. Here, as I said before, is our square number chart based on our multiplication chart, and we can find the area and the perimeter of squares, and then discern and discover the formula for area and perimeter of squares. Noting that we have 2 models for division, both quotative and partitive. I like to teach quotative first, making groups of a specific quantity, and then making groups. The reason is that partitive division, you must know your number facts, and our students who are still struggling with fluency will be totally lost. So we have to have some fluency and work with friendly numbers as we're discovering the concepts, then branch out. So linkages, and here's that linkage, multiplication to linear functions. This is a model for slope-intercept form. Constant rate of change by 2 and a starting value of 10. Students can build models for word problems, and then they can figure out and discover how they can code that slope-intercept form for doing word problems, write the equation of a line. And that's my first lesson in my algebra classes. We write the equation of lines from word problems before we ever graph anything, before we're ever even introduced to slope-intercept form. So strategies and models for fractions. We want explicit modeling of the concepts and the operations. We want precise, mathematically accurate language and multiple representations, first at the concrete level. We know from the science and many studies that students who only work with fractions from shading things in and doing pictures, they don't retain fraction concepts as well as students who cut and break things. So we want our students actively engaged in fraction work so that they really master those concepts. Those include in constructions, cutting things, breaking things, visual dictionaries for what is numerator, denominator, models of multiplication. For example, one I like to model with a number line is 6 times 1/2 versus 1/2 times 6. They get the same answer, but they look very differently. And it's important to know that for word problems. So they need number line work with fractions, lots of number line work, and lots of pictorial models. These are great opportunities for collaborative learning and discovery. So here we have multiple representations of fraction concepts. This is a fraction concept card illustrating the vocabulary. Students make these and they keep them in their binders. Here's a model with fraction tiles for fraction division, which we're going to talk about very briefly. And here we are doing a pictorial representation of simplifying 9/4. We color in the different fourths on a shape so we can see what that is, 9 individual 1/4 pieces. We put it on the number line, coloring each fourth, and then the mixed number underneath to make that connection. But they really need to understand fractions as numbers on a number line. That's critically important for higher level math. Multiple representations with fraction concepts. I love to use 2 squares of construction paper, and with those 2 squares cut into fourths and halves, you can teach all 4 operations with fractions using the appropriate language. Pattern blocks are also excellent, especially on a mat where you have ones and fractions of 1. Think about taking your students and using pattern blocks where the hexagon is your 1, the trapezoid is 1/2, the rhombus is 1/3, and the triangle is 1/6. If I take those pattern blocks and I put them on that place value mat, and I say I have 3 1/3. And I have to subtract 2/3. Do I have enough in my fractions of one place value? I don't. Where will I get what I need? Now, this is exactly replicating what we do with whole number subtraction. This is teaching from known to new. So I have to decompose one of those ones into thirds. Now it no longer can stay in that place value. It comes over here into the fractions of one place value. I now have an improper number. I have 2 4/3. And by the way, we always lay the new representation of the quantity on top of the old one to show its equivalence. Then that old one can go away. Now I have 2 4/3. I can subtract 2/3 and I can see my answer. So modeling with manipulatives is a very good way to transfer that to the abstract level. So pattern blocks get them out of those early grade references to 1/2, 1/3, and 1/4. And they really help our students to move back and forth between the representations, the number line, and digits and numerals. So keep in mind that we're using those multiple fraction representations, fraction tiles, concrete manipulatives, and shading. Shading numbers is great. I love some of the confidence building units on fractions from the Jump Math program. John Mighton's come up with some wonderful things in that. So we get to use some lovely activities here where students can build their fraction quantities. In 3rd grade, when I introduce fractions with manipulatives, the first thing I do, the first day, is use pattern blocks and have students build quantities, mixed numbers, improper fractions, fractions greater than 1, and I have them name them. As long as they can name that quantity, I'm very happy that they're beginning to understand fraction concepts and the vocabulary. So other things I want you to know about fractions is that your concise language, this is something that is mentioned in the practice guides for being necessary for students with special needs. They really must have fraction language, which is appropriate, that they can really master and apply. And if you teach the vocabulary in a way that they remember it, you won't have some of those common fractions mistakes. On my intake for my summer intervention, the most common one I see is 1/3 plus 1/3 is 2/6. So the first thing I'm going to do is I'm going to use clay. This is Crayola modeling clay, and it's sold in a box of 8 sticks for about $3 American. And I give each student 1/3 of a stick. We roll it into a ball, warm it up in our hands. Here, we place it on the place value mat, and then we start to do our fraction concepts. So I'm going to model just the first part of that for you. We're going to be using our ball of clay, a place value mat in a plastic sheet protector. I'm going to have them, I'm pounding this down. I actually made it a little bit too big. And we're going to roll it into a ball. We're going to put it in the ones place. Then I'm going to use my handy dandy fraction creator. Now my handy dandy fraction creator looks like that. It's a dental flosser. Once they have flattened that out into a circle, and the Rational Number Project many years ago said the first initial representation for fractions that was easiest for students to understand was circles. But using this model, we can do circles, rectangles, triangles, everything. We want to get them out of those circles at some point to really understand their fraction concepts. So this is my cookie. I'm going to divide my cookie to share it equally with a friend. and I'm going to divide it into 2 equal parts. And once it's in 2 equal parts, it's still the whole cookie, but its configuration is as parts. So here, I've cut it into 2 equal parts, and I'm going to use specific language. Each one is one of 2 equal parts. Its name is 1/2. It's a unique name like our teen numbers. And so when I have both of them, I have 2 of the halves. It's another name for 1. It's equivalent to 1. When I have more than 1/2, I have 2 halves. And just as in leaf and leaves, we find that the F becomes a V when it goes to the plural: calf, calves, leaf, leaves, half, halves. Now that sounds like a lot of language, but it's really necessary for some students to hear it over and over again so that they get that repetition to automaticity. We find that in terms of etymology, the numerator stands for num, or number, and it tells us how many of the parts we have. The denominator comes from the Latin root nam, or to name. It names the fraction part based on the division of the whole. I will cut that into 2 equal parts, this into 2 equal parts. And now each one of these is one of 4 equal parts. One of 4 equal parts. Its name is 1/4. And when I have all 4 of them, I have 4/4, which is equivalent to 1. It's a really, I take that, they cut it into eighths, roll the ball again, they cut it into thirds, but each time we're using that repetitive language for the conceptual awareness or the review and intervention. And our students continue to build. And then when we roll our ball again, we can shape it into a rectangle and cut it into thirds and sixths and ninths so that you can do an awful lot with the clay. And I'll tell you, in a middle school classroom reviewing fractions, you can hear a pin drop for 15 minutes. The students are so engaged. I've had 8th grade boys trying to cut that circle into 30 seconds. So it's a wonderful activity for students. I'm going to stop sharing that and go back to the presentation. And so here we have another activity for proportional reasoning. I've actually got this where we're going to say explicitly the yellow is one of 2 equal parts of the brown. The orange is one of 3 equal parts of the brown, but it's one of 2 equal parts of the black. Once we do a little proportional reasoning, then I'm going to say, if I have 4 cars and 3 trucks on the used car lot, how many is that in all? And they're going to say 7. I say 7 what's? It's 7 vehicles. We have to have a common name for a quantity. Well, in fractions, if I want to add the brown and the black, I have to reconfigure those quantities. And I want to find the common size piece that they share. I can cut the brown into yellow, but I can't cut the black into yellow. I can cut the brown into orange, and I can cut the black into orange. So when I convert the brown into 3 orange and the black into 2 orange, then I can add and achieve 5 orange in all. Getting rid of the numbers and using manipulatives is a great way to teach the concept of common denominators. And finally, here's our division of fractions. Remember when we used the strings with wings and we said 22 divided by 7, the remainder is 1 out of the 7 I need to make a new group? Well, in division, the remainder is always named in terms of the divisor, unlike multiplication, which is always named, the answer is named in terms of the whole. So if I had 1/2 of 1/4, how am I going to name it? So let's look at that very, very briefly and see some of the language that goes with division of fractions. So look at that for a moment. See how you would plot on a number line 1/6 groups of 1/2. How would you plot on a number line 1/2 times 6? Because with this one, we're going to divide each unit into halves and count how many halves we've made. On this one, we're taking the quantity 6 and dividing it into 2 equal parts, and you want one of them. So the answer in multiplication is always named in terms of the whole. If I multiply 1/2 of 1/4 and I get 1/8, 1/2 of 1/4, sorry, one of 2 equal parts of 1/4 is 1/8 of the whole. So in multiplication, the answer is named in terms of the whole. But in division, the answer is named in terms of the divisor. Remember, 22 divided by 7 is 3, and 1 out of the 7 I need to make a new group. If I take my fraction tiles and I want to know how many pieces the size of 1/3 I can make from 1/2, I see that 1/2 is bigger. I can make all of my third and some part of it more. And the answer is, what part of the third is my remainder? It is 1 of 2 equal parts of my third. So the answer to this problem of 1/2 divided by 1/3, because 1/2 is bigger, I can make all of it and 1/2 of another one. But if the quantity I'm dividing by is greater than my dividend, it's not how many of it can I make, it's how much of it can I make. So 1/3 divided by 1/2, I can only make 2 of the 3 equal parts of my half. I can make 2/3 of my half. You might want to rewind and watch that again. 1/3 is smaller, so I'm asking how much of my half can I make? And the answer is named in terms of the half. And I can make 2 of 3 equal parts of my half. Every teacher should be able to explain to their students why division of fraction works. We no longer use the keep, change, flip. We want to use multiply by the reciprocal. What is the reciprocal? And the goal of fraction division is to turn your divisor into 1 so that you're dividing by 1. So 1/2 divided by 1/3 is going to be, and here I'm going to use a grouping symbol. I'm going to multiply by the reciprocal. I'm going to multiply this by the reciprocal of my divisor. And I'm going to get 3/2 divided by, this is going to give me 1, because 3/3 is 1. And then our answer divided by 1 is itself. Now, what you don't need to remember is that we don't do this part in the algorithm. We just need to know why it works. So division of fractions, the answer is always named in terms of the divisor. We're almost through to the end here. So using concrete representations is really going to help our students. And using specific language, 3 groups of 1/2 is going to be 3/2. 1/2 of 6 is going to be 3. The language of math and fractions is critical. Here's that representation shown with pieces of construction paper. One is cut in fourths and one is cut in a half. Here we have, if I start with 3/4, how many halves can I make? I can make all of my half and half of another one. If I say, what is 1/2? 3/4 divided by 1/2. How many halves can I make? But if I do 1/2 divided by 3/4, look at this one. How much of the 3/4 can I make? I can make 2 of the 3 equal parts. This is a representation from a student where we did 5 divided by 3/4. And all I want to say about this one is that when we color in the groups of 3/4, we find that we can make 6 groups of the quantity 3/4. The 2 that are left over, my remainder, has to be named in terms of the quantity 3/4. I can make 2 of the 3, and that's why the answer is 2/3. So, finishing up here, unfinished learning with students. When students have gaps, they're missing foundation skills. It's really good to go back and review that content in the warm-ups or do now. Review it before applications, review it before problem solving so that they have some skills going into the problem solving task, and find ways to present that same material that's the unfinished learning, present it in new ways with manipulatives and precise language and conceptually based language, and practice interleaving for maintenance. The unfinished learning is not something that has to be taught wholly from the beginning because other teachers have planted those seeds. You only need to water them. Keep in mind that math is a hierarchy of concepts. It's vertical. So in order to go back from 3 minus 7 is -4, you might want to go back to numeracy and review those patterns and then apply that at the level of integers. Same thing with combining like terms. If you have special education students who don't know their add-ins of numbers under 10, go back and review one set and then use them in your integer applications and combining like terms. Always think vertically through your coherence map and think, what's the foundation skill that supports my grade level content? And let me see how I can go back to review that. Isolate that sub-skill, teach it, review it, and then apply it. So here we have the go to the 10 strategy, 9 plus 7, decompose 7 is 1 plus 6, bundle the 10 and add the rest. That same thing can be applied at integers with the visual imagery. So you can ask your students to go back and review that. Sub-skill practice here. What does it look like? X to the third and y squared versus x squared and y cubed. Why can't I combine those terms? They're both x's and y's, but the exponential values are different. When they can see it, they understand it. You can't just tell them. And combining like terms is the same as combining like place values. So you can go back and review those things with manipulatives. Our final tools include, if you have an inclusion class with many students who are weak in fluency, target a specific set of numbers for a period of time, review them, put them on a near-point reference at the beginning of class, and use them incessantly during class to build automaticity. The implications from the research are that multiplication is language dependent. That's different than teaching arithmetic fluency for addition and subtraction. I've given you the citation where you can find it. So scaffold your fluency development and review up through middle school if you have to. It doesn't hurt any student to review. And the more they retrieve it, the more they write it, the more they will remember it and be able to retrieve it. And it frees up working memory for your inquiry and applications. Students with dyslexia or language-based learning disabilities have trouble with the language of math. And that's why your language must be concise, repetitive, retrievable, because you're building the internal monologue for those students to work independently. Look for patterns within the times table chart. Chunk facts into meaningful groups for practice and daily work. Give them a blank times table chart and have them write those at the beginning of the period so that they can begin to use them during class and have them available. So use that blank chart, have them fill in only the facts you're using. I never give a child a completely filled out times table chart, and I don't use calculators in the classroom until the work gets really complex and the arithmetic gets really complex. For simple calculations, my students have to find their way and reason them out, but I give them tools for reasoning. Those visual near-point references and visual dictionaries might look like some of these. Here's one for geometry where they color in the postulates. Here's a fraction, decimal, and percent equivalence sheet where they draw a picture and relate those percentages and those decimal fractions to the fraction concepts for work. This is coding the parts of the quadratic equation. Graphic organizers are terrific for these kids. If you have an inclusion class, consider formatting with larger font and ample work and white space. Notice the repetition of numbers here. What is 5/10 of 800? What's 5/10 of 40? If they know that 5/10 is equivalent to 1/2, those are easy answers. What is 1/2 of 800? That same number fact is there. Give them ample repetition. And don't forget that gross motor movement. Reading large numbers for younger students, numeral formation, clapping the pattern of 5, doing cubic and quadratic functions in algebra yoga so that we can learn about vertical compression, vertical stretch, and flipping them over. All kinds of things can be taught with gross motor. So those gross motor movements, here's linear functions, quadratics, and cubics. And so everything that you can do with gross motor helps students to move. It gets them to breathe. It gets your class in choral alignment so that you can see who's got it and who doesn't. Those are formative assessments. Finally, your language needs to be mathematically accurate, concept-centered, concise, repeatable, and retrievable so that you build that internal monologue for them to work independently when they're away from you. And we just went over that language, how we link and the linkages from known to new, linking division of whole numbers to division of fractions, and why the remainder is named the way it is. So last and finally, warming up the brain here, your ESOL students, believe it or not, may be going home and doing their math in a second language, not English. Be aware of that. Be aware of your rate of speech. Be aware of using repetitive language when it's mathematically accurate so that you keep on building that vocabulary. Articulate clearly and link that language to concrete manipulatives so you're showing them what the word means. They're touching it and saying it to learn that English vocabulary. So our evidence-based strategies begin here, and that's the end of my presentation. In your handout, you're going to see these listed with the practice guides and what they say about them. So things like gross motor, targeted fluency, explicit instruction in concepts, not just drilling how to do a procedure, but what does the concept mean and what does it look like? And so here are the What Works Clearinghouse practice guides. I'm going to flip through these quickly because you'll have them in your handout. I'm telling you which practice guide it is, and I'm giving you what the strategies are, what the recommendations are from the evidence. And then I'm going to give you my contact information, and I'm going to give you my references. They will all be in the handouts. So I thank you for your kind attention. I hope that this presentation has helped you think about some new strategies and new models for those inclusion classes so that your students can achieve their very best math minds. Thank you.